All right, we've made it to chapter 3 in the textbook. This is our third unit in the calculus unit. And it's all about curve sketching. The whole unit is just curve sketching. So we're trying to take advantage of what we've learned with derivatives to help understand a little bit more about what our graphs will look like. Now you've done some of this in advanced functions already. In advanced functions, you paid particular attention to x-intercepts, y-intercepts, asymptotes, and end behavior. We need to deal with all of those still, and we're going to review those, so that's still coming up. We'll talk about that. The new stuff that we're able to do, though, which in a lot of cases is more important for a function, x-intercepts are just points, right? I mean, they're points on a graph. They have significance, obviously, but at the same time, they're just points that we can find. Max and mins are really important. So where does a graph actually reach a particular maximum? When does it reach its minimum value? That becomes very significant from an optimization standpoint, when it's useful to know when things are as big as possible or when they're as small as possible. This is supposed to be just for fun. I thought I'd toss it in here just in case you want to try it still. This is what we do in class. Usually I pull out the whiteboards and we say, try and do this. So you can, I don't know, I'd recommend it. I think it helps you with the problem solving aspect, just trying to pull this off. But I'll do it quickly here for you to try. So first thing I want you to draw is I want you to draw a function and it has to be cubic. So you don't have a whiteboard, I suppose you can just draw it on a piece of paper. So any function you want, but make it cubic. Okay, so draw that, see if you can make it work. Now once you've got that, you might need to change it now, but now I want you to see if you can draw one that only has one x-intercept. So all of these criteria must be met now. So still cubic, but now it only has one x-intercept. So change it if you need to. Okay. And I do want you to, don't just wait until I get down to number 7 and try and do it all at once, okay? Try and do one thing at a time. So once you've got 2 done, here's number 3. Now you need to make sure that the y-intercept is -4. So all 3 of those things have to happen. Okay, once you've got a picture that satisfies those 3, now we'll try number 4. Can you make that happen? It says f prime of -3 equals 0. So we have to understand what that means. Sorry, it's a little bit tricky to read. That does say f prime, so the derivative. The derivative at -3 is 0. So at x equals -3, what that means is that we have a horizontal tangent. So in this unit, we're recognizing when we're given information like that, or I should say more, when we find information like that, we have to recognize what it tells us. And the point of this exercise is trying to take all of the information that we might be given and put it into one function. Here's the next part. So we knew that when x is -3, we had a horizontal tangent. This is now saying that it must contain the point -3,5. So more specific, the point -3,5 has to be there. And at that point, we have a horizontal tangent. And remember, the y-intercept was -4, and there was only one x-intercept. So lots of things that we need to know. How about that one? It says f prime of x is less than 0 if x is greater than -3. And so maybe this has already happened, but what that's saying right here, if your derivative is less than 0, that means your slope is negative, right? That means your function is decreasing. So the graph has to be going downwards for values of x greater than -3. Notice I had to put greater than -3, not greater than or equal to, because we know at x equals -3, there's a horizontal tangent. And last one, that's a big one. Same sort of idea, it's giving you more information though. It says the first part, the derivative is less than, derivative is less than 0 for values of x less than -6. And the derivative is greater than 0 between -6 and -3. So to the left of -6, the graph is decreasing. To the right of -6, or I should say between -6 and -3, the graph is increasing. That's what that's telling you. So what does that mean happens at -6? Right at x equals -6, you'd have to have a horizontal tangent again. Okay, so see if you can pull that off. See if you can draw that. That's what it would look like. Okay. It's more of the note part. Fun over. How do we know if a function is increasing over a particular interval? So we know that a function is increasing. Increasing would mean the graph is going upwards, right? It's going up like that. That would be an increasing function. It's increasing if the derivative is greater than 0, right? If the derivative is greater than 0, then our tangent lines are positive. That's all we need to look at. And how do we know if it's decreasing? If the derivative is less than 0. How do you know if it's a horizontal tangent? The derivative is equal to 0. And if it's equal to 0, then you're going to have a max or a min. So we're interested in all these different possibilities. Well, that's all the possibilities, isn't it, of what the derivative could be? It could be greater than 0, could be less than 0, could equal 0. I suppose it could be undefined. So that's an extra possibility that we'll have to be a little bit careful of. Now, when we talk about maxes and mins, this is kind of a tricky idea. It's kind of a cool idea, actually. We have to compare this idea of a local max and a local min. There's a difference between a local max and an absolute maximum. So when we say a local maximum, it says a point is a local maximum if the y-coordinates of all points in the vicinity, and vicinity is a tricky little word from a math perspective, are less than the y-coordinate of the point. So let's pick out one here. Here is a local maximum right there. Because at that point, the y value, which is, I don't know, probably around 5 or so, right? It's higher than all of the other points in the vicinity. So when I'm saying the vicinity this time, I guess I'm talking about sort of, well, around here. Okay? Are there other places on the function where it goes higher than 5? For sure, right? Like this, all of this is all higher than -5. Or it's higher than 5, sorry. So 5 is called a local maximum. In that particular little area, right there, 5 is the highest we can get. Other places on the function, we might go higher. But in that little range right there, that would be our local max. Now compare that to a graph like this one. See if I can draw a good one, like, I don't know, something like that. And I picked this point right here. That's not a local max, because in the vicinity, there's points that are higher, right? Right beside it is higher. There's I can't draw it, right? It's too small, but the point right there is bigger. It's higher than the other one. So that wouldn't be a local max. So the issue with vicinity is we could actually be really, really, really tiny. So imagine I zoomed in on some other function like this, and I was like 0.1, and this is 0.0, whoops, that's not right. 0.11, so I'm like really close. You'd never notice this if you were zoomed out and say I had a function that looked like that. Okay? This here is still called a local max, right? Even though there's other points over here that are higher up. Because in this vicinity, so points a little bit to the left and a little bit to the right are lower. Okay? It's a tricky idea. Basically, it has to do with limits again, doesn't it? Like as you get close from the left and as you get close from the right, all of the numbers to the left and the right would have to be a little bit smaller. And if they're smaller, we'd have a local maximum. Compare that to, oops, didn't work at all. Here we go. A local minimum obviously works exactly the same way. So a local minimum occurs right here because points in the vicinity are higher than that point. There's other points over here that are lower, but I don't care about those because I'm calling this a local minimum. How can we find the locations? That part's easy. That was basically what we've done for the last 2 chapters, right? We can find local maxes and local mins because we have horizontal tangents there. And if we have horizontal tangents, that means that the derivative would have to be 0. So if I want to find a horizontal tangent, in order to find the local maxes and the local mins, we just set the derivative to 0 and solve. And that'll give us those locations. Okay, so those were our local maxes and mins. This is an absolute max. A function is an absolute maximum at a particular location if that value is, that y value, so if f of a is greater than all of the other y values in the domain. Okay, so the graph that I've shown you here has an absolute maximum. It has an absolute maximum right there. That's as high as the graph ever goes. I guess it's only showing a domain from here to, I guess, the 10, right? We're only considering values between 0 and 10 on the x-axis. But nowhere else in that domain do we see a higher value on the function. That's as high as it goes. This point here isn't an absolute maximum because there's other points that are higher up. So the green one's a local maximum, but it's not an absolute maximum. The minimum here is a little bit trickier to see. The local minimum's obvious, right? We saw that one a second ago. There's the local min. Is it the absolute minimum though? No, because right here, that point there is still lower. So this one here is called our absolute minimum. Based on the domain that we've picked. Now, based on that function, I think if we were going to continue it, right, further left and further right, it looks to me like both of those ends are going to go down forever. Okay, so if we were considering the entire function, the domain was all real numbers, then there wouldn't be a minimum at all, right? It would just keep going down forever. But because we've limited the domain, we're saying we're only considering values between 0 and 10, the absolute minimum happens when x is 0. What's interesting about that is that that's an absolute minimum. This blue one isn't a local minimum, right? This one's a local minimum right there. You can't really call the other one a local minimum, right? We wouldn't have found that point by setting the derivative to 0. So what we're going to have to do when we're trying to find absolute maxes and absolute mins, we have to look and consider all the locals, right? Places where we're going to have derivatives of 0. And then we also have to consider the endpoints, the point furthest to the left and furthest to the right, because there's a chance when we have those that they'll actually be lower or higher than where the local mins or the local maxes are. At the bottom there, a critical number. A critical number is the number that we would sub in so that we'd end up with a derivative of 0. So a is called a critical number there because f prime of a is 0. Okay, so a is a critical number. I don't use the term critical number very often. We're going to use the term critical point a ton. So a critical point is a point where we have a local minimum or a local maximum. Okay, so critical point is any point where we end up with a derivative of 0. Or I suppose sometimes we'll call it if the derivative doesn't exist there too. Really important points for this unit with our curve sketching. Okay, question here says, determine the absolute max and min of the function over that particular interval. So what I said a second ago is we need to consider two things. We need to consider our local maxes and mins, which now we're just calling critical points. Right? So that would have been the short form for me to write it. We're going to look at the critical points, and we're also going to look at the endpoints of the interval. So the endpoints are, we need to consider what happens at x equals -3 and what happens at x equals 5. That part's not hard because we're given those numbers. The critical points we have to find. So to find our critical points, we need to set the derivative to 0. So I'll find the derivative. Funny, after the last unit, now all of a sudden we're down to really simple derivatives again for a little bit. Just a nice little cubic polynomial. So there's a derivative. I'll set that to 0. And I'm going to factor. And that's just a difference of squares. And it's all set to 0. So therefore, x equals minus 3 is one solution. Oh, not minus 3. That's definitely a minus 2, isn't it? X equals minus 2 from the first bracket, or x equals 2 from the second bracket. Those are the critical numbers, right? Minus 2 and 2 are the values of x where we would get a derivative of 0. I need the points. So I would like to know f of minus 2, and I would like to know f of 2. So what that's telling me, basically it's telling me, I know that those are going to be maxes or mins. Right? I don't know too much else yet. It's a cubic. I do have the graph there. I'll show you that to you in a minute. We're just going to figure out how high these actually are. So forgive me, I got to put this in the calculator. Cubed. And hopefully not make any mistakes. I got 13 there, I hope. This unit, I can almost guarantee you that I'm going to make some calculation errors. So my apologies in advance. Hopefully I catch them. Got a minus 19 there. 2 minus 24. Yeah, I think that's right. So those are our values so far. So 13 is currently the highest value we have. Minus 19 is currently the lowest value that we have. And that was looking at critical points. So we've considered the critical points. Now we need to consider the end points. So we need to know what f of minus 3 is, because that's the furthest to the left. And we need to know what f of 5 is. That's the furthest to the right. Because what we're wondering is, do the endpoints actually extend higher or lower than the critical points, which is what we saw in this example. Right? We found our critical points. This one had 3. But it turned out that one of the endpoints was actually lower than the critical point we had. So that's what we're checking here. Minus 3 cubed minus 27 plus 6 minus 3. I got 6 on this one, so that doesn't win anything. That's right in the middle. 5 is going to be big though, right? 5 cubed minus 60. I get 62 for that one. I'm just subbing it into the function, right? Sorry, I didn't mention that. That's all I'm doing. We're figuring out the y value for particular x values. So based on this, we want to know the absolute max and the absolute min in those ranges, right? Oh, I should have mentioned, I suppose, too. Minus 2 and 2 do fit into the interval we are considering, all right? So in that interval, the lowest that we ever get, the absolute min, was the minus 19. Okay, that was the lowest we ever got. And that happened at a critical point. And the absolute max didn't happen at the critical point. The critical point was 13. That was as high as it went. But if we continued on with the function, it turns out that it went higher. It's going to get up as high as 62. Let's see if I can swing this. Oh, that wasn't what I wanted. Here's the graph. And hopefully it looks like I actually did that graph right then, I think. It doesn't go as far as x equals 5, so you can't see it on the graph. You can see how low it went. You can see right here, that's the minus 19 value, right? That was our critical point. That was our local minimum. But after that local minimum, it starts to head upwards again, and it's still on the way up. And what that's at, there's 3, there's 4, so 5's still over there. It's still on its way up. It's going to easily surpass that maximum of 13 that we had found. And that's what we noticed, was that the absolute max turns out to go up all the way up to 62. Okay. So that's the type of question there where we're finding absolute maxes and absolute mins. This unit is all about trying to graph well, trying to come up with a really good graph of particular functions. So here's our first one. We're not going to do too many cortex, but this is one that I really like because it looks horrible. And we want to do a few things. We want to try and find all the critical points. We also want to try and find x-intercepts. Y-intercept is easy. I guess I can do that first for us. By the end of this unit, we're going to find all kinds of information about particular functions. And what we're going to do is we're just going to build each day. So each day we'll add in a little bit more and go from there. By the end of the unit, our curve sketch, it's almost like we're going to have a curve sketching algorithm. We're going to do this, then we're going to do this, and this, and this, and this, and in the end, graph the thing, and we should be pretty darned accurate with that graph. So the y-intercept, all we do to get the y-intercept is we sub in 0, and that's always a really easy thing to do because everything cancels except the constant at the end. So my y-intercept is just -1. X-intercepts aren't always as much fun, unless you're a math teacher, and then it's lots of fun. To get the x-intercepts, we're setting the y value to 0, right? So notice I'm not even doing any calculus yet. This is still advanced function stuff. But this is maybe not so much fun calculus stuff, or advanced function stuff, because that looks pretty tricky to try and solve, right? So hopefully what you guys all thought of when you first saw it is you went, oh shoot, I know how to do that. We have to do that using synthetic division, right? Which isn't wrong, but I wouldn't have given it to you if we had to do that because it would have been really, really miserable. So there's a cool little shortcut to it. Not an obvious one by any means, but I liked it, so I wanted to show it to you. The one way to avoid synthetic division is factoring, and sometimes you can just factor it. And this doesn't look easy to factor, but it turns out it factors really nicely by grouping. The thing is I'm going to regroup. So I'm going to reorder it this way. X to the 4th minus 1. So I brought the -1 up there. Plus 2x cubed minus 2x. And I'm not sure if this is something that would have jumped out at you as something to do, but it just works so darn nicely. I wanted to show you. So the way grouping works is now we try and factor each piece. So we're going to factor the first 2 terms, and we're going to factor the last 2 terms. X to the 4th minus 1 is a fancy difference of squares. So it looks like that as our first term. The second term, well, it's not quite as nice, right? There's 2x cubed minus 2x. But I can common factor that. I can take a 2x out of both. So I take a 2x out. That leaves me with x squared minus 1. And the whole key to factoring by grouping is that I need to have something the same in both of these new groups once I common factor. So there's an x squared minus 1 in both. So to continue with the factoring by grouping, I'm going to pull that x squared minus 1 out to the front. And all this is, it's a massive common factor, right? That comes out. What's left from the first part was x squared plus 1. And what's left from the second part was 2x. And that's not too bad. So I've got x squared minus 1, x squared plus 2x plus 1. So by factoring by grouping, I've got to there so far. And I'm going to keep factoring. X squared minus 1 is another difference of squares. And x squared plus 2x plus 1 is a perfect square. It's x plus 1 times x plus 1, or x plus 1 squared. Which means I can simplify the whole thing to x minus 1, x plus 1, cubed. And maybe, hopefully, you remember a little bit from that advanced functions on what that exponent of 3 tells you. If not, we'll see in a second. But our conclusion from this, we were trying to find the x-intercepts, right? The solutions here are that x equals 1 or x equals -1. So those are our x-intercepts. It's not enough space. Those are our 2 x-intercepts at 1 and -1. So we found some good stuff so far. But we want to do more because I don't want to just know about x-intercepts. That would just be advanced functions. So I would like to know about critical points too. And now I've lost my function. This is going to be new for me because usually doing this unit, I would use all of the blackboards in the room. So we'll see how it goes. We'll see. We'll manage. We've got the y-intercept. We've got the x-intercepts. I want to get the critical points. So to find the critical points, I need to take the derivative and I need to set it to 0. So the derivative, again, nice, we just get to do, I don't know, some relatively easy stuff, I suppose. 4x cubed plus 6x squared minus 2. There's our derivative. That doesn't look nice at all, actually. What the heck are we going to do with that? The other one worked out so nicely. It's really hard, actually, to come up with a function that works after you take the derivative in on the original function. We need to set it to 0, right? Set that to 0. And I have a feeling that we're going to need, I have a feeling we might need some division on this one. Don't see a nice way to factor it. I could common factor out a 2, which will make our life just a tiny bit easier. But not a lot. Okay, if I'm going to try and solve that, it looks like we're going to have to use our factor theorem. Well, it's good for us to try, I suppose. We don't use it that often in this class, so it's good that we get a chance to review it. We want to find something that will divide into 2x cubed plus 3x squared minus 1. So we're thinking of, because we have to wonder, I'm not exactly sure how Mr. Vandenberg would have taught you this, but hopefully I'll come close. We're going to think of that function right there. And we need to think of what number we could sub in to get an answer of 0. And it looks to me like if we sub in a minus 1, that would give us minus 2 there, plus 3. Yep. So this is our factor theorem. It says if g of minus 1 gives us an answer of 0, therefore x plus 1 divides into the function. So that's good. X plus 1 will divide into it. Mr. Vandenberg probably told you that I don't like synthetic division. I don't have a great reason why I don't like synthetic division. I just don't. So you guys will probably be able to do this much faster than I can. It's okay, I'll race you. I'm going to divide x plus 1 into 2x cubed plus 3x squared plus 0x. Don't forget to put that x term in, minus 1. And if you don't want to see the long division, you want to do synthetic, just ignore me. X plus 1. So that's going to be 2x squared There we go. It worked out great. So the factor theorem came through for us. That's good news. 0 equals, the 2 is still there. I don't actually need the 2. It's not that helpful. X plus 1, we need to divide it in. And 2x squared plus x minus 1. Okay, we're doing good. We're doing good. Can we factor that last one? I feel like we can. We would need two numbers that multiply to minus 2 and add to 1. That'll definitely work. So 2x squared plus 2x minus x minus 1. I'm just doing some factoring here. You guys might have different methods of factoring. The method I'm using was called decomposition. I'm going to change colors just so you can see what I'm doing. Factoring out a 2. Oops, excuse me. Factoring out a 2x from that first bracket. This is more factoring by grouping right here. There we go. That was a lot of work actually to factor that. We had to use our long division, and then we had a tough trinomial to handle still too. We end up getting to here though. So we've done well in the end. Assuming I haven't made a calculation error, which, man, I'm hoping I haven't. Remember, we're finding our critical points, right? So our solutions were x equals minus 1, and this other one, 2x minus 1 equals 0, which means x is equal to a half. Those are our critical numbers. Those are the locations where we're going to have critical points. We have horizontal tangents at x equals negative 1 and at x equals a half. Now, I got to scroll back. This has become a pretty long page, I think. At x equals negative 1, that was one of our x-intercepts. Right? Oops, slow down. Right? That was one of our x-intercepts. So not only is it an x-intercept, it's also a critical point. The derivative there is going to be 0. But now we have this other critical point at 1/2. So I think I would like to know what f of 1/2 is. I'd like to know what the actual point is. And now I've lost the function. What was the original function? I'm going to sub 1/2 into this equation right here. Sorry, bear with me for a second. 0.5 to the 4th. Oh, I got a really ugly number. It's good for you to see it, actually. We're going to get some ugly numbers in this unit. I do my best so we pick some good ones. But I had to save the good ones for later on when we have to do even more difficult calculations with them. I got that. So our y value is minus 1.6875, which we're graphing it, right? So there's no way we're being that accurate. That's going to be around minus 1.7, and I'm going to hope for the best that I can come close to graphing that point. Okay, I'm going to skip ahead. Here's my attempt at graphing the thing. And I'm probably going to have to back up a little bit just so I can see a few different things. We found two x-intercepts, right? An x-intercept at minus 1 and an x-intercept at 1. And we just found that critical point, right? That critical point, I'm going to, whoops, too far. Too high. Oh. That critical point was at 0.5 minus 1.7. So 0.5 minus 1.7-ish, around there or so. Okay. Now, that point, the blue one, and I'm gonna color this one blue too. Those are both horizontal tangents, right? They're both horizontal tangents. was what it looked like when we factored it. So I think the second one, if that's a horizontal tangent, that's relatively easy to see what's going to happen. It has to look like that, and it's going to come up through the red, and it's just going to keep on going, right? It goes straight up. We know that it goes straight up because there's no more critical points to the right, so it's never going to reach another horizontal tangent. It just keeps going. It's a lousy curve. It looks like it's curving the wrong way there. It just keeps going straight up like that. Further over to the right, further up. It's that second point, the one on the left, that's tricky, because of that blue guy, right here, I need a horizontal tangent. But if you remember some stuff about quartics, the end behavior on the left and on the right should be the same. And this one has a positive coefficient here, right? It's positive 1 there. So a quartic like that is supposed to look something like that. The key is here and here. It's got to be pointing up in both cases. So when I mentioned earlier, it's how much do you remember about the fact that this is a cube there? And if it's a cube, what it does is it runs through here, and to create the horizontal tangent, instead of doing that, doesn't do that. It's like this is a triple intercept, sort of. So it goes through, creates a horizontal tangent like that, and then shoots up. Okay, that's what the graph looks like. We were able to graph that with relatively little knowledge actually so far. So we've only found 3 things. We found intercepts. I didn't put the y-intercept. What was the y-intercept? Was it -1? It was. I can make that a little bit better. There we go. There. That's not bad. So we've graphed this with relatively little information. Trickiest part, as I say, was this point right here. So if you didn't remember that x plus 1 cubed part, not to worry, because in a couple days we're gonna, within a couple days we're gonna look at other ways that the derivative is gonna tell us what's going on at that point. Makes it even easier than having to remember that formula. Okay, so there's our graph. Here's the actual result. So that's the real one. That's graphed on Geometer Sketchpad, and you can see how close we came, right? So we did quite well to be able to get that looking that way. Throughout this unit, we've got to look at lots of these. We're going to spend some time on just polynomial functions, but then we're going to get into rational ones as well, where there's going to be asymptotes that we have to deal with, so lots of other considerations too. Okay, but good start for us here. We'll spend some more time looking at critical points, and coming up we have to look at inflection points, which are points where we change concavity. Okay, so lots more to come.